So we are discussing the kind of questions that are asked in GATE examination from the topic of kinematic chain and mechanisms. So I'll take you through some more examples on the subject. Typically, a mechanism would be given, and then the sketch of the mechanism will be given in the paper. So I'll take a sketch as our example. So consider this mechanism. A mechanism is drawn here, which is having various kind of links. Like this one is a quaternary link, these are the ternary link. However, as we saw in our earlier example, the type of link is immaterial for determining degree of freedom of the mechanism. It's only the type of the joints which matter. So the question asked here is that how many unique mechanisms can be obtained by this kinematic chain. So first thing towards solving this problem is to find out the degree of freedom of the mechanism. That itself may be a question. For that, we'll just label the mechanisms, various links in the mechanisms, 1, 2, 3, 4, 5, 6, 7, and 8. So as you can see here, it's 8 links in the mechanism. Now we'll count the number of joints. So we have rotary joints, the pin joints. The count is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 joints, and we need to consider the class of the joints also. So all of these are rotary joints. So all of them are class 1 kinematic pairs. So by applying the Grubler's criterion, the degree of freedom of the mechanism would be 3 multiplied by number of links minus 1, that means 8 minus 1, minus 2 times number of class 1 joints, that is 10. And we don't have any class 2 joints here. So the degree of freedom is 1. So hence there exists a definite relation between motion of different links in this mechanism. Now the question asked here is that how many unique mechanisms can be obtained from this kinematic chain. So if you go to the definition of mechanism, you see that the mechanism is formed by fixing one link in the kinematic chain. Okay, so the question asked here is how many unique. So this is a catch in this question. The question asks us for the unique mechanisms. So just one straightway answer would be that there are 8 links in the mechanism. So there, by fixing one link at a time, we can form 8 mechanisms. But the catch here is that it's asking for unique mechanisms. So that's why we have to consider for symmetry. Now in this kinematic chain, you can see that the link number 2 and 4 are identical. Similarly, the link number 8 and 6 are identical, and link number 1 and 5 are identical. So if you fix 2 or if you fix 4, you are going to get essentially the same mechanism. Similarly, if you fix 8 or 6, you are going to get same mechanism. So by fixing any of these links, 1, 5, 2, 4, 8, 6, you can get a maximum of 3 mechanisms. And now, what are the other links remaining? That is link number 3 and link number 7. So you can get 2 more links, 2 more mechanisms by fixing link 7 or 3. And three mechanisms by fixing 1, 8, 2 or 6, 5, 4. So there are total 5 unique mechanisms can be obtained from this kinematic chain. So the answer is 5. We'll take up one more example. I'll just sketch the mechanism for you. The mechanism shown here as a special thing in this question is that a CAM mechanism is involved. So I'm sketching the CAM mechanism right now. Question asked is determine mobility of mechanism. So we will go forward for solving this problem by using our usual Douglas criterion approach. So I will number the mechanisms 1, 2, 3, 4, 5, 6. However, there is one more link here, that is ground. So in a kinematic chain example that we have considered till now, as you can see from our previous diagram, there was no ground involved, only a kinematic chain was given. But in this problem, the ground is also given. So we can consider ground as a one single link, that is link number 7. So it is very important to remember this point while solving the problem. If you forget to take count ground as one of the link, then you will count a wrong number of links, and through the Douglas criterion you will get a wrong answer. So totally we have 7 links here. One of them, the link number 7, is fixed, that is the ground. Now we will count the number of class 1 joints. So you can count here class 1 joints, that is 1, 2, 3, 4, 5, 6, 7 and 8. So class 1 joints are 8 rotary pairs, and we have one CAM joint. Now the degree of freedom of a CAM joint are 2. So it's a class 2 mechanism. How the CAM is having 2 degree of freedom? Like CAM is resting on a flat surface. The CAM can have a rotary motion and it can have a translational motion. So 2 degree of freedom are allowed. So CAM is a class 2 joint, a kinematic pair. Therefore, the number of class 2 joints is 1. Now we will substitute these values in the degree of freedom formula, the Douglas criterion. So that is for planar mechanism 3 times the number of links minus 1 is 7 minus 1, minus 2 times class 1 mechanisms, number of class 1 mechanisms, that is 8 here, minus 1 times the number of class 2 joints, that is 1 here. So if you calculate this, you will get 1. So the mobility of this mechanism, that means the degree of freedom, is 1. Now while solving this example, you have come across a joint of CAM. So we know the degree of freedom of a CAM mechanism. In some cases, such as like for testing the aptitude, there will be questions like you will be given some different kind of element in the mechanism, such as spring or a sliding joint or a CAM. So in those cases, we have a powerful concept called equivalent linkage that can be used to simplify the problem. So I'll just illustrate that example for you. So for example, like in a mechanism, if you get a spring, so say two elements in a mechanism are connected by a spring. Then how to go about it? So as you can see here, you have to see the mobility of the joint here. So it can move in translational direction up and down. Similarly, the bottom one can travel the up and down in translational motion. So if you replace this spring by two links, two binary links, you can see that you can get similar kind of motion of the joints. So this is equivalent linkage of a spring. So two binary links. So in your problem you can replace the spring by two binary links and you can go forward to solve it with our usual Grappler's criterion approach. Similarly, for the sliding pair, so if you sketch a sliding pair here, so this sliding pair is, this sliding joint is having 1 degree of freedom in the translational motion, while the crank is having the rotary motion. This problem can be simplified by visualizing a 4-bar chain. The 4-bar chain is a very important kinematic chain which we will consider in much more detail in coming slides. So here there are 4 links joined together by rotary joints, and one link can rotate. So if you see the motion of this, you can just visualize the motion of this link in a rotatory fashion. Similarly, likewise, correspondingly, this link will also rotate. However, if you make the length of the link, length of this link infinity, then the rotary motion of this link at this point will appear almost like a translational motion. If the radius is infinity, then it will almost appear as a translational motion, because the displacement L here is given by L is equal to r theta, where theta is the rotation. So if r is infinity, for a finite L, you need to have theta tending to 0. So it's almost like a translational motion. There is no angular movement involved. So that is why you can replace the sliding pair by a binary link. So there is a binary link here which is joined to two other links. So you can replace the sliding pair by binary link. The degree of freedom of binary link is 1, and degree of freedom of a sliding pair is also 1. So in some cases it may help you to simplify the problem. Similarly, for the cams, we have 2 cams resting on top of each other like this. So they can be visualized as a combination of one binary link, that is this, combined by 2 rotary pair. This is one rotary pair, this is one rotary pair, pair means joint, this is another rotary pair. So if you make an arrangement like this, the cams can do rotational motions with respect to each other. This cam can rotate relative to this cam. This cam, one of the cam can be a flat surface. That is the general example of cam that we see. And this cam can also move in the translational direction. So cam can be replaced by one binary link and on both sides of the binary link you have 2, like on either side you have each, so you have 2 rotary pairs. So these kind of concepts you can keep in your mind, like in some cases if there is a tricky question, you can simplify it and get the solution. So now we will move forward to a very important topic in the theory of mechanisms, that is the 4-bar chain. The 4-bar chain is shown here on the left hand side with the means of an sketch. It consists of 4 binary links and 4 revolute or rotary pairs. So this is the basic version of a 4-bar mechanism. However, as we move along, we will see that the type of pairs can be changed to other class 1 pairs. So the revolute joint is a class 1 pair, so it can be changed to other class 1 pairs. And the nature of links can also vary. So it is the basic chain and it is building block of many other complex mechanisms. So by arranging various 4-bar chains in various manners, multiple degrees of freedom mechanisms can be obtained. If you see from the mobility perspective, you can visualize that a 2-bar chain lying in space may not serve any useful purpose. So there is 2 elements hanging in space. If you even fix one link, the other link just hanging in space by itself may not give any useful output. To form a 3-bar chain, then the degree of freedom is 0 here. There can't be any movement. This is a fixed linkage. And if you go to 4-bar chain, here you can see that there is definite relation in motion between different entities. This link can rotate. Likewise, it will have a corresponding motion of this link, or you can fix the other links and get different kind of motion. That's why the 4-bar linkage is of very much importance and attention. 4 is the number of links which gives 1 degree of freedom. So it is a minimum number of links, which gives 1 degree of freedom. So we are interested in 1 degree of freedom because 1 degree of freedom means a definite relation in movement which can be calculated. That's why we are studying this mechanism. The necessary condition for forming a 4-bar chain is as follows. We see that we have a 4-bar chain marked here. So the shortest link we will mark its length as S. The longest link we will mark its length as L. And the other 2 links, anyone you can mark as P and other one you can mark as Q. So like that you have length of these 4 links. The condition for formation of 4-bar chain is that the length of the longest link should be less than the sum of the shortest link and the length of the other 2 links. The sum of S, P and Q, S plus P plus Q, should be greater than length of the longest link. If it is just equal, you will get a mechanism like this. The length of the longest link and all the other 3 links lying on the longest mechanism. So it is barely useful. So no meaningful mechanism will form like that. And you can't have the length of the longest link greater than the sum of all the other 3 links from simple geometrical consideration. So this is a condition for formation of link. So this is always satisfied if you can draw a diagram like this. It will be obviously satisfied. So now we will see the nomenclature of the 4-bar mechanism. The link AD shown here, that is connecting the joint A and D, is known as the fixed link. The link AB, this is normally regarded as the input link from where the energy input or the motion input is coming, that is usually through a motor, and this is called input link. The link 3 CD, this is normally called a follower or output link. The motion comes as a input from AB, which is also called the driver link, and the motion goes as output to CD, which is the output link or the driven link. So these definitions are just for our for laying out a framework for our further theoretical work. Any of the links can be exchanged. The input can be made output by supplying motion to it, and vice versa. If the input link is able to make a complete revolution, then it is known as a crank. So in a slider crank mechanism, this is we get motion from a crank. This is what is ordered crank. If the input link is not able to make a complete rotation or revolution and able to make only a rocking motion or oscillating motion, then it is called a rocker or oscillatory link. The similar definition also applies for the output link. So if the output link is able to make a complete revolution, then it is known as crank, and if the output link is able to make only a oscillating motion, it is called a rocker or oscillatory link. So based on the length and geometry of a 4-bar mechanism, the explanation of which we will cover in coming slides, the mechanism can be classified as a crank mechanism, crank rocker, or CR mechanism, and a rocker mechanism based on input and output. So now we come to a very important condition in 4-bar chain formation, that is called Grashof condition. It basically checks the link proportions. So it checks the geometry of the link, length of the links, proportion to each other, and then based on that it classifies the category of chain mechanisms. So a particular category of mechanism is having freedom for a particular kind of motion that we will be seeing shortly. The basic condition for Grasshoff's criteria is that the length of the longest link plus the length of the shortest link must be less than the length of the sum of the length of the other two links. If this is satisfied, then the mechanism is called a Grashoff mechanism. Grashoff's mechanism or a class 1 mechanism. So what is special about a Grashoff's mechanism is that it allows continuous relative rotation between two members. So if the Grashoff's condition is satisfied, one of the links in the mechanism, so which is typically the shortest link, will have a complete rotation. So it can have complete 360-degree motion. So it will be like a crank. So at least one crank in the mechanism. So from that you can get CC arrangement, crank arrangement, or crank rocker arrangement. So this is a condition. So how this Grashoff's condition is derived? It's again from simple geometrical consideration. Consider a mechanism, core mechanism here, as we just discussed. So this is a shortest link, this is the longest link, these are the intermediate. If you want to have a complete rotation of shortest link, the extreme position of this mechanism would be such that the shortest and the longest link fall in a single line. That time, if the shortest link were to have a complete rotation ahead of this angle of -180 degree, then the links P and Q should allow it to come to this position of angle 180 degree. If the length were shorter of the link P and Q, then the S would have stuck somewhere in some angular position, and so this is the case where the Grashoff's condition is not satisfied. In this case, you can clearly see from the law of the triangle that this is forming one triangle. So in a triangle, sum of any two sides, that is P plus Q, is greater than the third side. The third side is L plus S in this case. So S plus L is less than P plus Q. So that is the condition being satisfied here, and full rotation is possible. While in case the P and plus Q is not greater than L plus S, it is less than L plus S, the complete rotation is not possible. It will get somewhere in some angular position, so it can only have a rocker arrangement, a rocker motion. It cannot have a crank motion, complete rotation motion. It is not possible. So that is how the Grashoff condition is determined. For the cases where sum of length of shortest and longest link is greater than the sum of the lengths of other two links, those mechanisms are called non-Grashoff mechanisms or class 2 mechanisms. So such kind of mechanisms can result in only rocker arrangement. Whereas in the earlier case we saw that the crank and the crank rocker arrangements are possible. So there is a crank in the arrangement. There is again a third special category where the sum of the shortest and the longest link is just equal to the sum of the other two links, length of other two links. These are called spatial Grashof mechanisms or class 3 mechanisms. These kind of mechanisms result in parallelogram connections. You get a parallelogram geometry. So I'll be sketching all these mechanisms in detail, and you get a double crank or drag link mechanism. So I'll be drawing sketches and explaining you about all these mechanisms in detail later.